Figure 15.17b also shows a value known as the CP statistic, which measures the difference between the true population model and regression model derived from the sample data. The goal is for the CP statistic to be less than or equal to k plus 1, where k equals the number of independent variables. Our highlighted subset in figure 15.17b also meet this criterion, which is summarized in table 15.11. Both of these models will provide roughly the same level of performance when predicting the number of weekly cell phone activation for an employee. When faced with such a choice, the more desirable model is the one with fewer independent variables. This results in a final model that requires less data and has a smaller chance of multicolority wreaking havoc on the regression. Therefore, using the best subset method, our preferred choice is the model that includes the independent variables x1, x2, and x3. You can find the regression model for this subset in another worksheet labeled 3x. Because this subset is the first one listed in the group of 3 independent variables in figure 15.17b. These data are displayed in figure 15.17c. According to figure 15.17c, our final activation regression model is as follows. Y cap equal to minus 3.8522 plus 0.8415x1 plus 3.7355x2 plus 0.3297x3, where x1 is the employee's number of years of experience on the job. x2, the gender of the employee, 0 for male and 1 for female. x3, the employee's performance rating on a scale of 1 to 100. Suppose Verizon would like to use this model to predict the average number of weekly activation for a male employee who has a performance rating of 85 and 4 years of experience on the job. Our best subset model predicts the following. Y cap equal to 27.5 activation per week. Notice that the best subset regression method arrived at a different final model than the general stepwise regression that was discussed earlier. This can occur because the best subsets method will often find a combination variable that the general stepwise method never examined. There is also the possibility that the subset with the highest adjusted R-square might include independent variables that are not statistically significant with p-values greater than alpha. For instance, the gen variable in 15.17c has a p-value equal to 0.0668. The model builder might need to decide which is more important, significant independent variable or the highest adjusted R-square. As we saw in figure 15.17b, there is often more than one appropriate subset from which to choose. Table 15.12 compares the best subset and general stepwise methods for our cell phone activation example. The adjusted R square for the general stepwise method can be found in row 16 in figure 15.17b. Other selection methods. Two additional stepwise regression techniques are available through PA-STAT that are similar to the general stepwise regression method. The first method is known as forward selection regression. This method follows the same steps as the general stepwise method in that it began with no variables in the model. The forward selection method also uses the p-value to enter criterion to determine if an independent variable is eligible to be part of the model. The major difference in these two techniques is that once an independent variable enters the forward selection model, it can never leave. As a result, you may end up with independent variables in the final model that are not statistically significant. You can select this method in PA-STAT stepwise regression dialog box, which is shown in figure 15.16a. Another stepwise method is known as backward elimination regression. Here, we begin the process with all of the independent variables in the model. Using the p-value to remove value provided by the user in the dialog box, independent variables are selected to leave the model one at a time. Once an independent variable has been banished from a backward elimination model, it can never come back in a later step, which with backward elimination, you can be assured that all the remaining variables will be significantly significant. This method can also be found in PA-STAT's stepwise regression dialog box shown in figure 15.16a. Because forward selection and backward elimination are stepwise models that look at the perfect of one independent variable at a time, there is no guarantee that the final model will find the group of variables that provides the highest possible adjusted R square. However, just as with the general stepwise procedure, both these methods can examine a large number of independent variables as possible candidates for the final regression model. Residual analysis. The last step of the model building process is to conduct a procedure known as residual analysis. In order for the result from multiple regression analysis to be reliable, certain key assumptions need to hold true. Interpreting regression output without regard to this assumption may lead to misleading conclusions. These important assumptions are as follows. 1. The residual for the regression model have a constant variance. 2. The residual follow the normal probability distribution. 3. The residual are independent of one another. 4. The relationship between each independent variable and the dependent variable is linear. As you can see, The majority of these assumptions focus on the residual, which is just a fancy word statisticians use to describe the difference between the actual and predicted values of the dependent variable. In other words, we can describe the residual as a type of regression error. For example, the first employee in the activation 2.xlxx data file had 19 activation with a performance rating of 80, had 1 year of experience, and was male. Our best subset regression model predicts the following number of activation for this employee. Y cap equal to 23.4 activation per week. The difference between the actual and predicted activation can be found using equation 15.15, where EI is the residual of the ith observation in the sample. Yi is the actual value of the dependent variable for the ith data point. Y cap I is the predicted value of the dependent variable for the ith data point. The residual for this first employee using equation 15.15 is as follows. EI equal to E1 equal to Y1 minus Y cap 1 is equal to 19 minus 23.4 is equal to minus 4.4. In other words, the regression model predicts that the first employee will have 44.4 more activation in a week than he actually had. Using Excel data analysis toolpack, we can find the residuals for each observation in our samples. Mac user can find this instruction using phstat on the textbook website. We will demonstrate this procedure using the Excel file activation 3.xlxx, which contain the independent variable from the best subset regression model. The steps are 1. Open the Excel file activation 3.xlxx. 2. Go to Data, then select Data Analysis as shown in figure 15.18a. 3. Select Regression in the Data Analysis dialog box and click OK. 4. Fill in the regression dialog box as shown in figure 15.18b and click OK. Because we check residual in the dialog box, Excel provides a residual output table listing the residual for each observation in our sample. Figure 15.18c shows this output. Negative residual indicate that the predicted cell phone activation are more than the actual activation for each employee. Positive residual reflect the opposite condition. The closer the residual are to zero, the better the fit of the regression model. Our first assumption for the multiple regression model is that the residual have a constant variable, which is also known as homoscedasticity, a term we introduced in chapter 14. Because we check residual plot in the residual box, the Excel regression output provides a residual plot for each independent variable so that we can examine if this condition is being met. Figure 15.19 shows the residual plot for the exp variables. Each point in this plot represents the residual for each employee plot against the number of years of experience on the job for that employee. Recall that the first employee in our sample has a residual of minus 4.4 activation. This employee also had 1 year of experience. The points shown in the red circle in figure 15.19 correspond to this employee. The multiple regression model assumes that the variation in the residual along the horizontal axis in figure 15.19 is fairly constant. In other words, the error in the regression model for employees with little experience should not greatly differ from more experienced employees. This condition of constant residual variance across the exp variable appears to be satisfied as we examine figure 15.19. Notice that the data points are randomly scattered around the horizontal axis in the residual plot. I'm sure some of you are wondering how the residual plot would appear if this constant variance condition was not met. Figure 15.20 shows a hypothetical case of such an instance. Notice that the regression error is much larger for less experienced employees when compared with those with more experience. We can draw this conclusion because the data in figure 15.20 have residual values closer to 0 as we move toward the right side of the horizontal experience axis. According to this figure, an employee with 10 years of experience has a residual very close to 0, meaning this model does a good job in predicting activation for more experienced employees. Compare this with the residual for an employee with 2 years of experience. As you can see, the prediction errors are farther from 0 on this end of the plot. This pattern suggests that this model is more accurate when predicting the number of activation for experienced salespeople when compared with less experienced salespeople. Thus, this residual plot does not appear to satisfy the condition that the residual have a constant variance. Figure 15.21 and 15.22 show the residual plots for the other 2 remaining independent variables from our original example, perf and gen. Again, the residual for the first employee minus 4.4 from our sample is circled in red in both figures, with a performance rating equal to 80 and a gender dummy variable equal to 0. There does not appear to be a blatant violation of the constant variance requirement in either figure. Although it does seem that the male employees have a little more error in the regression model than the female employees. You can tell this is so because the points are spread out farther from the x-axis for the men than they are for the woman. The second assumption for the multiple regression model is that the residuals follow the normal probability distribution. We can investigate if this assumption holds true by inspecting a normal probability plot, which graph the residual of the y-axis and the residual z-score on the x-axis. If the residual follow the normal probability distribution, the data in this plot will fall approximately on the straight line. Figure 15.23 shows the normal probability plot for the activation data, which appear to follow a straight line. Based on this figure, we can confirm that the residuals follow a normal distribution for this data set. See the textbook's website for instruction on how to construct this normal probability plot using PHStat. Also, if you inspect in figure 15.18b, you will see an option in Excel regression procedure to generate a normal probability plot. However, this option, for some strange reason, generates a plot for the dependent variable which tell us nothing about the distribution of the model's residual. Thank you.